This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. So this is our first video, and the purpose of this course is to teach you the physics that you need to succeed in a diagnostic medical sonography program. And so to get started, the first thing we want to do is look at the concept of medical imaging in general. As you already, I'm sure, know, diagnostic medical sonography, or what I'll often refer to just as ultrasound, is a way to image the human body. It turns out that there are a number of different non-invasive imaging techniques that are currently used in medicine. And so we're going to just go through each of these so you can get a sense of where ultrasound fits in the overall medical imaging picture, and also so we can understand why we need to know physics to be successful in a DMS program. Let's start out by talking about X-rays. This is probably the medical imaging that we're all most directly familiar with, because most of us have had an X-ray at some point in our lives, whether it's at the dentist or if you've ever broken a bone, for sure then you've had X-rays. The key thing about X-rays is they use high-frequency electromagnetic waves. And so one of the things that we're going to have to understand in this course is what are electromagnetic waves. We want to understand all of the physics behind these imaging technologies. High-frequency electromagnetic waves are often also referred to as ionizing radiation. And later on in the course we'll learn about what that means. So X-rays use high-frequency electromagnetic waves, and they're very useful for things like diagnosing bone fractures, dental issues. You may also be familiar with the fact that they're used for lung infections. For example, older folks often need to get a chest X-ray to be diagnosed to see if they have pneumonia or not. So X-rays are certainly a very common type of medical imaging. The next type we want to look at is what's called computed tomography, or CT scans. The first thing we want to understand about CT scans is they are simply an advanced X-ray technique. They actually use higher doses of X-rays. So again, electromagnetic waves, high-frequency electromagnetic waves are what we refer to as ionizing radiation. But they provide a lot more detail than a standard X-ray. This concept of a scan also is sometimes referred to as a slice. And that concept of a slice is also called a cross section. And so what you'll notice is that when we look at a CT scan, we're literally looking at slices of a particular part of the body, or one plane of that part of the body. The image here on the left are the CT scans of someone's head. And so you'll notice it's literally giving us a picture of a cross-section of the head at different places as it goes through the head. This is a CT scan of somebody's core abdomen, and again, it's actually giving these cross-sections or slices. And so higher doses of radiation or ionizing radiation than in an X-ray, but also get more detailed images. And these can be used for diagnosing things like tumors, internal injuries, complex fractures, and also heart and vascular disease. Another common type of medical imaging is called magnetic resonance imaging, or MRIs. And the first thing we want to notice here is that MRIs still use electromagnetic waves, but you'll notice that they're low frequency. And of course, we need to understand what we mean by high and low frequency, and we'll certainly cover those in this course. But low frequency electromagnetic waves are also known as radio waves. In other words, the same thing that brings radio stations or TV stations through the air. MRIs are used primarily to look at soft tissue. And If you've ever had a knee injury or a hip injury, you may have had an MRI. I've had a few MRIs on my knees over the years because it allows the doctor to actually be able to look at not only the bones but the cartilage that's in the joint itself. And so MRIs are used for things like diagnosing strokes, tumors, blood vessel issues, but probably most commonly looking at muscle and ligament and tendon issues in joints. The next type of medical imaging we want to talk about is what's called a PET scan, or positron emission tomography. You'll notice that, first of all, we have the word scan again. And so what that means, again, is that it's going to show you slices of the object that you're imaging. What's different in a PET scan than a CT scan is that a radioactive tracer is used. And so what happens is the person is either injected with a tracer or they swallow the tracer, and then the output of that radioactive material is what's being used to create the images or the scans. And so PET scans can be used for diagnosing cancer, heart disease, Alzheimer's, seizures, epilepsy, Parkinson's. You'll notice really specifically here, often we're talking about imaging the brain when we're using a PET scan. And finally, we get to ultrasound, or diagnostic medical sonography. Notice the key thing here we want to pay attention to is that ultrasound does not use electromagnetic waves. Ultrasound uses sound waves. So they are high frequency sound waves, and in fact that's what ultra in ultrasound means. It means frequencies above human hearing. Later on in the course we'll talk about the range of human hearing and what frequencies that we can hear, but the sound waves that are used to form images with ultrasound are at frequencies above what we can hear. So if you have an ultrasound transducer and you're using that to produce an image, you're not going to hear a sound because it's above the frequency that humans can hear. Probably the most common form or the common use of ultrasound that you're all familiar with is monitoring pregnancy. We get these nice images of the baby while they're inside the womb, and that can be used to monitor and make sure everything is going fine during the pregnancy. But ultrasound can also be used to diagnose gallbladder disease, breast lumps, genital prostate issues. It can also be used to evaluate blood flow. And when we're evaluating blood flow, specifically, we're using something called the Doppler effect. And we'll be talking about what the Doppler effect is when we talk about waves and sound. But it's a special thing that happens with waves that allows us to look at flow within the body. Another use of ultrasound is to guide biopsies. So if a doctor is using a needle to go in and take a sample of something that is suspicious, it might be something like a tumor, they've got to make sure that they're getting the needle into exactly where they want to get the sample from. And that's another use of ultrasound, is to guide those biopsies. So why do we need to understand physics when we want to simply learn to be an ultrasound technician? Well, a lot of the terms that we've already used so far in this video are physics terms, things like frequency and electromagnetic waves and sound waves. And so if we're going to understand these different imaging technologies, and especially if we're going to understand ultrasound, we do need to understand physics. So let's talk about what physics is. If you look up in the dictionary, you'll find that physics is defined as the study of the basic principles that govern the universe. And you may also find it will say something like study of matter, energy, and forces. By the term matter, we simply mean the stuff that everything is made of. And then energy and forces have to do with how that stuff interacts. So with physics, we're covering everything from the very small, from subatomic particles, all the way up to the structure and the history of the universe. In other words, physics studies what happens inside the atom. We know that atoms form molecules, and molecules form all of the everyday matter that we experience, such as ourselves and the objects that are around you right now. But inside the atom, we have electrons, and then we have the nucleus of the atom. The nucleus is made up of protons and neutrons, and it turns out that protons and neutrons themselves are made up of more fundamental particles called quarks. So in physics, we're understanding how it is that quarks bind together to form protons and neutrons. How do protons and neutrons bind together to form the nucleus of an atom? Why do the electrons bond to the nucleus to form the atom itself? All of that is covered by physics. If we look at the large-scale structure of the universe, that's also governed by physics. So why is it that the Earth orbits the Sun? Well, we know that that's due to the force of gravity. But in physics, we study not only what's happening in our own solar system, but how the universe itself is structured. So you may be familiar with the fact that the Sun is just an average star. So when you look up at the night sky and you see all those little bright lights, those are all suns that are out there. And so our Sun is just an example of a typical star. Our Sun is part of the Milky Way galaxy, and we're right about here in the galaxy. We're about 2/3 of the way out. The Milky Way galaxy itself has over 100 billion stars in it. So the Sun is just one of 100 billion stars that makes up our own galaxy. What's mind-blowing about that is that the Milky Way is just one of more than 2 trillion galaxies in the known universe. So physics is learning or is studying everything from the very smallest stuff that's going on to the very largest stuff that's going on in our universe. Here, obviously, we're concerned primarily with what do we need to understand from physics to be successful in a diagnostic medical sonography program. So let's look at that. Well, we want to be able to understand medical imaging in general and then ultrasound imaging in particular. The areas of physics we need are the following. First of all, we need to understand motion. The area of physics that involves motion is called kinematics, and kinematics describes how objects move. So in kinematics, we talk about things like the position of an object, or an object's velocity, or an object's acceleration. We also need to understand something about dynamics. Dynamics is the area of physics that talks about why motion changes. So for example, why does an object speed up or slow down or change direction? Those are all examples of an object whose motion is changing. And it turns out that the reason the motion of an object changes is due to force, and Newton's laws of motion describe how it all works. And so that's another area of physics we need to understand. We also need to understand the concept of energy. Energy is one of the most useful concepts in all of science because it turns out that energy is conserved. So conservation of energy is one of the fundamental important topics in all of science, not just physics. Just to give you an example of why we need to understand energy, it turns out that waves can carry energy. So when you are sending sound waves into somebody's body to perform an ultrasound image, you are sending energy into their body. Well, we need to understand then how does that energy interact with human tissue? In other words, how do we know that doing an ultrasound on a baby is safe, that we're not hurting the baby in some way by sending that energy into the baby in the form of sound waves. So we need to learn about the different types of energy, how energy can be converted from one type to another, and especially for us, understanding the concept of thermal energy and heat transfer. We also need to just understand fundamentally how matter works. So we've already alluded a little bit to atoms and molecules. We know that everyday materials can be in one of three states. They can be in solids, liquids, and gases. So we need to look at the details of that. It turns out that liquids and gases can also flow, and with liquids and gases, we also get the concept of pressure. And so we need to understand those concepts as well. An example of this would be blood pressure. So in the human body, we know that the blood flows throughout the body, pumped by the heart. And one of the most common measurements that's made in a medical environment is measuring somebody's blood pressure. So how does that work? What does it mean to have a blood pressure, let's say, of 120/80, which would be a typical blood pressure? And so in this course, we'll look at the underlying physics that explains fluid flow and pressure. Now, the most important topic for us is going to be talking about vibrations and waves. We've already said that ultrasound is using sound waves. So clearly we need to understand sound waves because that's what ultrasound is. But we also want to understand the different types of medical imaging. So for example, we've said that electromagnetic waves are used in X-ray, CT scans, and MRIs. And then we just need to understand the properties of waves in general, whether we're talking about sound waves or electromagnetic waves, and how do those waves interact with matter. So for example, how is it that just by sending a sound wave into somebody's body, we can form an image of what's going on inside their body? Well, all of that has to do with how the sound wave interacts with that tissue and whether it gets absorbed or reflected back. That's how the ultrasound machine is going to be able to come up with an image of what's going on inside the body. So we've got to be able to understand all of that. Finally, we need to understand the basics of electricity and basic circuits because we want to be able to understand a little bit about, for example, how does an ultrasound transducer actually create a sound wave? Or how does it detect the sound wave on reflections coming back and ultimately form the ultrasound image? Now, to understand physics, we actually have to understand something else, and you probably know what it is. That is math. So think about math. Math is the language of physics. Right? Math is how we actually communicate a lot of what we learn in physics. For example, one of the laws that we're going to learn is Newton's second law. Newton's second law says the net force on an object is equal to the mass times the acceleration. So that's an example of how we use an algebraic expression to represent a physics law. Now, when we have an algebraic expression, often we need to be able to rearrange it. For example, if we want to solve for the acceleration, we need to be able to take that formula and rearrange it so that we have the A on the left and the net force and the mass on the right. And so we'll review the basic math and algebra that you'll need to be successful in a DMS program. We need to be comfortable with measurements, and therefore we need to be comfortable with the metric system and unit conversions. So basic measurements in the metric system, we know we measure length in meters, mass in kilograms, time in seconds, but there are a number of other units that you're going to need to be comfortable with as you go through the program, and so we're going to cover all of that. And we also need to be comfortable with unit conversions. For example, if you're told that a length was measured to be 50.0 centimeters, we need to be able to convert that and say that is 0.500 meters. So unit conversions are important. Finally, we also need to be comfortable with scientific notation, because when we're working with the human body, we're often working with very big or very small numbers. Just as an example of that, the number of atoms in the human body is amazingly large. So it turns out that it's about 7 times 10 to the 27th, and that is writing a number in scientific notation. So scientific notation is a shorthand. What does that mean? Well, that means a 7 followed by 27 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Now, I'm never going to write out a number like that again in the course, but I wanted to do it once just to show how inconvenient it would be to have to write out all of those zeros. You can see that this is a much better way to do it, just to write down a number that represents how many zeros there are, because this would certainly not be very practical if every time we were dealing with large or small numbers we had to write them all the way out like that. And so in the first part of the course, we'll do a math review, we'll talk about the metric system and unit conversions, and we'll cover scientific notation. So all of the videos in this course will cover all of the information that we've introduced here today, everything from all those areas in physics, the basic math that you need to be successful, and most importantly for all of you watching this video, how that physics relates to medical imaging. And so that's our goal.